Welcome to the Peacademia course on the basics of semiconductors. This lecture covers the current density and band diagram of a biased PN junction. Let's start. By the time you finish this lesson, you will learn the ideal PN junction current density equation, voltage drop equation of a PN junction, benchmarked voltage drop current density diagrams of 4 different semiconductors, and the energy band diagram of the PN junction under forward and reverse biasing. In the past 2 lectures, I have gone through the current flow mechanisms of the PN junction under forward and reverse biasings. Following up on those discussions, in this lecture, I will explain how we can formulate the current flow in a PN junction under forward and reverse biasing, and the biasing effect on the energy band diagram of the device. We already labeled the total current density of the PN junction by J. J equals Jp plus Jn. For an ideal PN junction, the current density J is obtained using this equation. This equation is valid under both the forward and reverse biases. If you have followed all the previous lectures on this course, you are then familiar with all the parameters used in this equation except Js. Js is called the reverse saturation current and is obtained using this equation. As you can see, the reverse saturation current depends on the intrinsic concentration Ni, diffusion constants dP and dN, diffusion length Lp and Ln, and the dopant concentrations Na and Nd. I already talked about the diffusion length Lp and Ln. In case the definitions of Ln and Lp are not yet clear, please watch the previous lectures of this course. The diffusion constants dP and dN are themselves functions of the charge carrier mobility mu and temperature. As far as I'm concerned in this course, it is enough to know what the reverse saturation current is and what parameters affect its density. In practice, you can find the quantity of the reverse saturation current in the datasheet of the device. By the way, Js is a very small quantity. This diagram shows the normalized current density versus the normalized voltage applied to the PN junction. Under the reverse bias, Vd is negative. For a very small reverse voltage in order of a couple of thermal voltage, the negative current through the PN junction becomes constant. In other words, it is saturated. We already called this current the reverse saturation current Js. If Vd equals 0, the current density is 0 because the PN junction is in the equilibrium state. If Vd is larger than 0, the current exponentially increases. What this diagram demonstrates is that this device rectifies current. This means it allows the current to flow in only one direction. Under the reverse bias, the reverse saturation current is so small that we can neglect it in most of the situations. We can manipulate the current density equation to compute the voltage over the PN junction Vd. Vd equals Kt over Q times the natural logarithm of the normalized current density plus 1. For a non-ideal diode or PN junction, we need to add the effect of the electrical resistance of the P and N neutral regions. Here the neutral region resistance is shown by the small r. As I mentioned earlier in this lecture, Js is a function of Na, Nd, Ln, Lp, dP, and dN. For the sake of our future calculations, let's imagine these quantities for these parameters. The question that we can ask is that how do we calculate the built-in voltage of the diode using this equation? To do so, we need to determine a threshold current density, using which we can say the diode is fully turned on. Joseph Lutz and his colleagues in the book entitled Semiconductor Power Devices considered 5 ampere per centimeter square as the threshold current density. so I use this number. By doing the calculation, the built-in voltage diagram for the germanium, silicon, gallium arsenide, and 4H silicon carbide based PN junctions is obtained. The built-in voltage for a germanium diode is 0.26 volt, for silicon 0.65 volt, for gallium arsenide 1.09 volts, and for 4H silicon carbide 2.77 volts. This diagram benchmarks the current density VD curves of 4 different PN junction diodes. In general, we desire the built-in voltage to be as small as possible to reduce the conduction loss. Therefore, our choice among all these semiconductors might be the germanium. However, if we focus on the third quarter of the diagram, we find that a smaller built-in voltage results in a larger reverse saturation current. Among all the semiconductors listed, germanium has the largest reverse saturation current. Large JS makes the thermal management of the device a nightmare, especially in power electronics applications. Among these 4 semiconductors, 4H silicon carbide has the largest energy gap, and therefore its built-in voltage is the largest and its reverse saturation current density is the smallest. I hope you remember this energy band diagram of the PN junction. In the equilibrium state, we studied this energy band diagram, but I did not explain what happens to the energy band diagram under the forward and reverse biasings. The difference between this energy band diagram and the one you saw in the previous lectures is that here I'm showing not only the top and bottom of the valence and conduction bands, but also the bottom and top of the valence and conduction bands. The depth of the bend in the conduction and valence bands is Q VBI when the device is in the equilibrium state. However, when it is biased, we can rewrite it as Q times VBI minus VD. VD is the externally applied voltage. First, let's agree to analyze these energy bands in equilibrium. If you look at the conduction band of the N semiconductor, you'll notice that the top of the conduction band is at the same level of the bottom of the P semiconductor conduction band. Even if there is an electron in the N semiconductor that is excited enough to be close to the top of the conduction band, it cannot overcome the barrier to go to the P semiconductor. If I increase VD but negatively, I'm putting the PN junction diode in reverse bias. Negative VD causes the energy bands to bend more. If the barrier potential was Q VBI in equilibrium, it is now Q times VBI minus VD. Under this condition, overcoming the reverse bias potential barrier is much harder for electrons in the N semiconductor. Since under the reverse bias, the reverse saturation current flows through the device, unlike the equilibrium state, the Fermi level is broken. Let's resume everything back to the equilibrium state. What I want to do now is to increase VD, but this time positively. This makes the potential barrier smaller. In this case, the top of the conduction band of the N semiconductor is now within the boundaries of the P semiconductor conduction band. If there is an electron in the N semiconductor which is energetic enough to be close to the top of the conduction band of the N semiconductor, it easily overcomes the barrier and can go to the P semiconductor. If I further increase VD so that it becomes equal to the built-in voltage, the depth of the band is completely gone, and free electrons in the conduction band of the N semiconductor can move freely to the P semiconductor. The same thing also happens to holes. Holes can now freely move from the P semiconductor to N semiconductor. Under the forward biasing, the Fermi level breaks too, and the reason is that there is a current flow in the device. In this lecture, I discussed the ideal PN junction current density equation, voltage drop equation of a PN junction, and the energy band diagram of the PN junction diode under the forward and reverse biasing. In the next lecture, I will discuss the avalanche and Zener breakdowns. Thanks for joining this lecture of Peacademia.